Assalamualaikum and welcome to this is lecture number 7 officially of the online distance learning for after the lecture for the machinery course, and this is actually chapter number 4 I have over here with me. So this is chapter number 4. This is for the synchronous generator. I will be using this acronym SG over here every time. So whenever I use this word SG, this will actually means that I am asking for synchronous generator and nothing more. This is chapter number 4, and today we will be actually covering the basics of synchronous generator, and we will also make the equivalent circuit of a synchronous generator. But before we move on forward, what is this synchronous generator? As the name suggests, this is a generator, and this is going to generate an electrical energy from the mechanical energy. So certainly this is going to be beneficial as an electrical point of view. So it's going to take some mechanical source. So when it is going to take some mechanical source, so this means there is always going to be involved a prime mover. So when there is going to be a prime mover involved, so this means you are going to have a prime mover, and that's going to rotate some rotor, and you are going to have some output as an electrical energy. Now, since this is the AC machines part of the midterm which we are talking at present, so certainly this means that this prime mover is going to actually be a mechanical source, and the output of that generator which we are talking about here, as the word called is synchronous generator, is going to be an AC generator. Now, if you go back a little before your midterm course, in which we discussed about the DC machines over there, and we talked about the DC generator. In DC generator, the output was DC. Either it was a shunt generator, or either it was something series generator, or any other stuff of generator. It was a DC generator. This time we have an AC generator. Now, before I move on forward to the synchronous generator and what it is made up of, the problems of a DC generator, if we go a little bit 2-3 minutes on that one. If you remember, there was a field winding, and across that field winding, inside it there was a conductor. That conductor was placed inside a magnetic field that was being provided by the field windings, and you were getting an EMF induced inside that wire. Now, to get that EMF out of that wire, you required approximately a system of commutator and carbon brushes. So in DC machine, the very big problem was actually a commutator plus carbon brushes, and these were the actual problem over here. So when you had a commutator and you had a carbon brush, so this means that you were actually having problems, and the efficiency of that generator was not more than 60 to 70% of the whole over there. So there was a big loss over there. You were actually wasting 30 to 40% of the power over there, because you have to take out power from a rotating mass, which is actually the rotor over there. So when we talk about a synchronous generator, when we use the word synchronous generator, in synchronous generator, we are going to change this. How we are going to change that is that this time the field which we used to produce on some poles, and this time this field winding which we are going to have for the magnetic field over here, that magnetic field is going to be produced on a rotor. Now, how this will work, we'll just get it on a little bit time afterwards. So this field windings are going to be on the rotor. So this means that the field which is going to be given to this generator, same thing, no change over there, is actually going to be on the rotor over there. But the other windings, which we normally use the word armature winding, in which that were used on the rotor. So if the word is the armature windings, in which the EMFs are going to be, they are done on the stator. Now, what you have done actually, you have interchanged these two. Now, in DC machine, field windings were static, the armature winding was moving. This time, in synchronous generator, or simple SG, what you have done, you have interchanged this. The field windings are now rotating, and the armature windings. Now, you all know that the armature windings are actually the main windings in which the current is actually going to be produced. So when you are going to have the main EMF produced on the stator, you can take that current out of the armature windings very easily and without any carbon brushes. But still, that does not solve the problem. The problem is this, that the field windings are on the rotor now, but you still have to give some DC current to that rotor winding which are done on the rotor, so that now you have some magnetic field produced, and that magnetic field will be rotating as from a mechanical source which we have called as a prime mover. So the field windings are done on the rotor now. So still you require now carbon brushes, but this time remember one thing, since this is rotating, if you remember in DC machines anything was rotating, you were using carbon brushes and commutators, and because of that commutator and carbon brushes you were actually changing the direction of the current going inside that rotor after every half degree rotation or 180 degrees of rotation. This time you are going to use some slip rings, so that those slip rings are going to be on the rotor, and the rotor is actually going to be letting you the current flowing inside the rotor over there. That will be a constant DC current flowing depending upon whatever magnetic field you require, but that magnetic field is going to be produced by a constant DC, so you don't need to change the direction of the current in the rotor. So if I draw a first piece of a synchronous generator picture in front of you, it is going to be exactly again stator, and in the stator over here, again I'm assuming that this is a two-pole machine, so I have a stator winding such way that I have this stator windings over here, and in this stator winding, and if I change the little color over here just for the audience so that it's easy for the other ones. So when you have a rotor over here, the rotor is going to be again a circular object, and on this rotor you will be having again some windings, and this is the cross-sectional view. I hope this does not create any problems for the audience. So when you have this rotor over here, this rotor is going to be producing a magnetic field in such a way that it is going to be having supposedly a north pole created here and a south pole created here. So maybe the half of this is the rotor, it's a two-pole rotor, so you are going to have a magnetic field being produced. You are supplying this DC current to this rotor over here, and because of this north and south pole you are going to have an EMF induced inside this three-phase windings on the stator. Because if you remember your three conditions of your generator phenomena, the first condition was you required a magnetic field. So the first condition is it that you require a magnetic field. The second condition is this, that there should be a conductor placed in that magnetic field. So there should be a conductor in the magnetic field. The third condition is it that there should be a relative speed between the magnetic field and the conductor. So say the three conditions are fulfilled over here. How? This conductor over here, which we are going to call supposedly as A, and this is A dash over here. If you have gone through the induction motor, you are familiar with this, that this is A and this is A dash, because this is going to be a three-phase device again. So this one is A, and if I mark this with another color over here just for the difference over there, this will be B, this will be B dash, and if I use another color over here for the C winding, so this will be C and this will be C dash. I hope everyone is clear that why this is A, B and C by 120 degrees displaced over there, because this is a three-phase generator I'm talking about. So if for this conductor, which I am highlighting at present, for this conductor over here A, if you are having, sorry about this, so if you are having an A conductor, that A conductor is going to feel if this rotor is rotating in this anti-clockwise direction, the A conductor is going to feel that it is moving in the opposite direction. So the magnetic field is already there, the conductor A is going to feel it's going in the opposite direction. So what you are going to happen, there is going to be a dot introduced in this A conductor, and just opposite to this one there will be a cross, and similarly for this C dash and B dash there will be a dot, and in this C and B there will be a cross over there as well. So what is happening or telling you that there is a cross and dot formation. Now you can go through this one using your right hand rule yourself. So right hand rule, because this is for the generator. So you have the 3 fingers over there, so you can point out in the relative velocity vector direction, this is that B over there, this is that B over there, and certainly you can find out the direction of induced EMF E inside this one. So this is a synchronous generator. This is a very simple synchronous generator. You are providing a DC current over here inside this north and south pole rotor over there. This north and south pole have certainly been caused because of some cross and dot currents being produced over there. So this cross and dots are over here. You can make this cross and dots very easily over here by using your crosses and dots current flowing out. This is a cross-sectional view in front of you. So certainly this is going to be the magnetic field produced inside it. Now, if we talk about this one, this is very easy. Nothing changed over here. In induction motor, if you remember it, you were applying a 3-phase supply to your stator over here, and you were getting a revolving magnetic field. This time, you are giving a magnetic field to the rotor, and that rotor is going to rotate with the speed, and that is certainly going to be fixed, because if you remember, the formula was Ns equal to 120 F by P. Now in this formula, what you find out, you plugged in the frequency of 50 Hertz, and you got over here supposedly a 50 Hertz supply, which is standard in Pakistan. So the number of poles supposedly is the minimum is 2, so you get out approximately a 3000 RPM machine. So this means that you are actually having a synchronous speed of approximately 3000 RPM. Now this time, this is vice versa case, if you want a 50 Hertz supply to be produced by this stator over there, you want your rotor to be working at 3000 RPM over here, then you are going to get 50 Hertz. So you can analyze from this point of view, because this is a synchronous generator which we are talking about. So one thing very important which I forgot at the very start, synchronous generator is also called as an alternator. Synchronous generator also called as an alternator, because this is the device which is actually used for producing alternating current over here. So alternating current is there. So this is an alternator. So for an alternator in which you want to have a 50 Hertz supply being produced, depending upon whatever voltage is being produced over there, you will require approximately 3000 RPM. If you go a little wayward from that 3000 RPM limit, certainly the frequency will change. So you can analyze from this point of view that all the power generated at any power stations in Pakistan or anywhere all around the world, they will require a constant speed. So speed is a very, very critical factor. So if either supposedly you are at a Mangla Dam, Tarbela Dam, or maybe any powerhouse, maybe a steam house or steam turbine over there, speed is going to be very, very critical. And certainly, as this formula actually tells you from here, that you are going to have your speed and poles in the inverse relationship. Now that inverse relationship is actually coming on from here. So this is Ns is equal to 120 F by P. So if you just change this one over here, you can find out that your frequency is actually directly proportional to your speed, and it's inversely proportional to your frequency as well over there. So you have this Ns is equal to 120 F by P. So this is a simple synchronous generator producing you the 50 Hertz output waveform from the stator. So A, B and C phases, they are going to produce a 3-phase supply out of it. Now generally speaking, the DC machines, if you remember, which you did before your midterm, they were all having a DC output, but practically there was an AC induced inside them. But by the use of commutators, you changed them, you rectified them, and you converted them into a DC output. So if there were like many coils arranged in the whole spatial 360 degrees, so you were actually, what you were doing, you were actually rectifying them into DC, and it was a little bit ripple DC over there as an output, or in the output you were having a constant averaged out DC available over there from a DC generator. So practically in DC generator, you're also producing an AC waveform, but you are actually rectifying it by the use of commutators and carbon brushes over there. So here you don't need any carbon brushes or commutator, yes, but they are required because you are giving the field winding on the rotor, and the rotor is actually an electromagnet. So you are going to apply some like 1 ampere or 2 amperes of current to the rotor, and on the stator side A, B and C phases you are going to get approximately an output depending upon number of turns on the winding, depending upon the how they are arranged. They are certainly going to be double layer windings over there. I'm not going to go into details of the winding designs over there. That is totally separate course for that, but just for the purpose, the stator windings over here in this case, which are this A, B and C phase windings, they are actually the armature windings in which the EMF is going to be induced, and you can just take these 3 wires out from here, A, B and C phase, and these 3 phases can be actually used to power anything. Supposedly there is a step-up transformer over there, or maybe they are directly being used to some supply over there. So this is something. Okay, now since we have talked about the synchronous generator, the first thing which we go on first of all over here is this, that how many types of synchronous generators are there. So the first thing first over here, as you can see in this previous diagram, the stator is very same, and it is exactly the same stator just like an induction motor. So nothing is changed over here. The only thing that is going to be changed in the 2 types are actually the rotor over there. So the first type of a synchronous generator, which we call it over here, is called as the cylindrical rotor over here, and the second type is called as the salient pole rotor, or you can call it as a salient pole synchronous generator. So this one is also called, also as the name given, it is also called as the non-salient sorry about this. So this is called as the non-salient pole over there. Okay, so now you have these 2 types over there. Now what does this mean actually? As the name suggests over here, cylindrical rotor, this is the very same as this one. So cylindrical rotor, the rotor is cylindrical in shape over here. It has the uniform air gap. Certainly it's not that uniform over here as you can see, but this is actually just because of the drawing freehand over here. So certainly the air gap is actually going to be uniform. But when we are talk about a salient pole rotor, a salient pole rotor is going to be very different. So if I supposedly draw a first stator over here, let me draw that stator over here first. I hope this is going to be a better okay, sorry about this. Okay, so if I have another color supposedly just for okay. If the stator is there, the rotor in this case is actually going to be like this, and if let me just complete it, the previous stator slots. This is the first slot, sorry, the stator slots A dash, B dash. So these are the A, this is A dash, this is B, this is B dash, this is C, and this is C dash. Now the rotor over here, as you can see, it's just a simple bar over there, and on this bar certainly you are going to have a winding, and that winding is going to supply that DC current over there. So certainly there is going to be some DC current supplied over there, and if you see your right hand rule over here, if this is the current direction, I am using the conventional current flow, so the flux is going to be produced inward outward of here, and that's going to return back. So this is going to be the south pole. So you can see this type of rotor, which is called as a salient pole rotor, as you can see over here, is actually going to be made up of 2 bars or a single bar which has a protruding shape over there. The word salient actually means, in the literal meaning form, it's called as protruding. So this is actually coming out over there. Now what is the advantage of this rotor on compared to the other rotor? Certainly they both have some advantages and disadvantages. Now if you can see very easily over here, this cylindrical pole rotor, it has an advantage, it has a uniform air gap. But the problem over here is that when you are going to make this rotor is going to be made again of these slots over there, and in these slots you are going to place some conductors over there. Now practically, if you want to have a rotor which has approximately more than 4 or 6 poles, the number of these slots over here in which the windings are going to be placed is going to be quite large. So mechanically it's not going to be very good or stable thing, so that the rotor is not going to be made mechanically robust. So practically, when you want to have more number of poles, you are going to use the salient pole. Now what is the advantage and how you are going to make it? For example, if you want to make supposedly a 4-pole salient pole rotor, you are going to, I'm just going to draw the rotor over here for your over here. So this is my first pole, and in this first pole you have this is the over here. So supposedly this is the north pole and this is the pivot. I'm not going to draw the windings over here just for sake, and this is my second pole, and so this can be the south pole, this can be the north pole, and this can be the south pole. You can draw the windings also. Now you can see this is a 4-pole salient pole machine or a salient pole rotor in front of you. Now if you want to add over here maybe more number of poles, you can add another bar over here, you can add another bar over here, and this can continue to go on as far as you have more number of poles over there. Just to tell you or give you an idea, the salient pole rotor being used at Tarbela is a power plant in Pakistan. All of you must have heard about it. The generators which are used over there, they are salient pole machines, and the number of poles is equal to 36. So you can see, imagine over there will be certainly 36 poles protruding out over there. So number of poles is 36 over there. Now the question here arises that what is the advantage of actually having 36 number of poles? Now 36 number of poles, if I go a little bit into it, since we did just the formula that you already are familiar, that 120 F by P, Ns is equal to 120 F by P. Now when you have 120 F by P, if I just rearrange this one over there, this is my number of frequency is equal to NSP divided by 120. This is my frequency over here. Now when you have Ns and P, they both are actually inversely related to each other over here. So if I supposedly want to have a chart in which I want to maintain this frequency as 50 Hertz, if I want to make this as 50 Hertz, what is the minimum number of poles? I will have 2, then I will have 4, then I will have 6, and so on. And certainly for number of poles P to number of poles equal to 2, and you have the synchronous speed, it has to be approximately 3000. This is certainly RPM over there. If you have a 4-pole machine, then you are going to have 1500 RPM required. So this is the condition for the frequency to be 50 Hertz over there. So if you have 6 poles over there, then you require approximately 1000 RPM. So certainly, just imagine if I continue to increase this and make this equal to a 36-pole machine. So what will be the answer? Let me just show you on this one. So this will be approximately, since this is equal to, the formula is NSP by 120 over there. So what speed I require over here for this purpose, this will be 50 multiplied by 120 over here, and since number of poles is 36, so this will be equal to 166.666 over there. So this means that for 36 poles, 166.67 RPM. So this is the speed that is required at the Tarbela Dam, so that you can actually produce that frequency over there. Now 36 poles, the number of poles are large, so this means practically you will have a lot amount of rods like this arranged over there. So 36 protruding poles. Now since the poles are large, what happens? The speed is small, and this is mechanically very good. Why? Because when you are going to have 36 poles over here, you are going to have a lot of air gaps. So when you have a lot of air gaps over here, what this means actually, that it is not mechanically balanced. So it cannot move at a very high speed. On the contrary, when you are going to have something a cylindrical pole, as you can see over here in this case, this is the two-pole cylindrical rotor. So what you are seeing over here, this is having a uniform air gap on all sides, on all 360 degrees. So this means that it can run at a high speed. There is no mechanical imbalance over there. There is no air gaps over there, as contrary to what you are seeing over here in this 4-pole, or maybe it can be, you can call it as 8 poles, or you can increase it to 36 poles, just like the Tarbela Dam one. So this means that you cannot run it. So practically, when you are approximately in the range of 2 or 4 poles, this is the region of the salient pole machines. This is the normal trend. So whenever you are going to run for a steam turbine, and where are steam turbines? Steam turbines are at Capco, steam turbines are at Hubco, steam turbines are at Sahiwal coal power plant. They are all steam turbines. What they do, they burn the fuel and they produce the steam. Either the fuel can be coal, it can be oil, or it can be anything. So you are having that 3000 RPM or 1500 RPM. So you must have heard about it, that steam turbine generators or powerhouses, they require some time. They require some time to maintain that speed, to maintain that pressure, so that then they can actually supply the output. On the contrary, these, if the number of poles are large and they are going to go towards 36, maybe even more than that, they give you an idea. If you go on towards the Wikipedia page and you go on towards the Hoover Dam page, you will find out that number of poles over there for that are approximately more than 40 plus over there. And you can see the Hoover Dam rotor as well over there on the Wikipedia page. Now this is used for the sorry about it, I forgot, this is not for the cylindrical pole, sorry, I forgot, this is the cylindrical pole, and this one is for the salient pole. Sorry about it. So this is the two formations over here. So when you are going to have a 2-pole or 4-pole, you have cylindrical poles over there, and when you have more than 4, maybe you have the 6, 8, 10, so on, up till maybe like 40 even. But certainly increasing the number of poles has other problems over there. You have to do windings over there. But the advantage is good, that you only require a very small speed over there, that is 166.67 RPMs over there. So technically speaking, there are two rotors which are required in a synchronous generator. One is called as the salient pole. They also have a DC windings on it. The cylindrical pole one also has the windings on it, but they are specialized winding inside it, so they are only used for 2 poles or 4-pole machines. Maybe for 6 poles it can also be made, but it will not be that mechanically robust over there. So when you have a cylindrical pole, you can use it for steam turbines, because the speed is something to 3000 to 1500 RPM. Or when you are going to have it for 6 poles and so on, you can go on towards the salient pole. Now before I move on forward, now the problem over here, the next problem before I move on towards the equivalent circuit, is this, that a synchronous generator still has one big problem, which we discussed in the very start, that you require slip rings, and inside those slip rings, or with those slip rings, you have carbon brushes which are constantly sliding. Now when you have a very small generator, maybe that is powering something, a UET, or maybe something just a hospital or some other emergency facility, that is okay, well and okay, no issues with that. But when you are going to have a generator of approximately 1000 megawatts, just like a generator at Tarbela, the maximum generator over there is 1400, or I guess 2000 is the latest one that is added over there, then you cannot afford carbon brushes and slip rings. For that purpose, the very important thing is this, that you have to avoid those carbon brushes and slip rings, because they are going to be a serious form of efficiency loss over here. So what the first thing first over here, what you will do is that the first technique is this. Okay, so the first thing first over here is, this is called as a pilot exciter, a brushless exciter over here, sorry about it. This is called as a brushless exciter. Now what you are seeing over here in front of you is actually a diagram of a synchronous generator, in such a way that you have a rotor and a stator over here. Now if I just zoom in and over there, this over here, this area in this region over here is called as the, let me just use the other ones over here. So this one is the rotor, and this one is the stator over here. Now you can see over there, instead of just the main one, there are actually a lot of other things over here. The main generator is actually this one and this one. So if you see over there on the rotor, you have a main feed. This is that same winding which I am talking about over here, which is actually the DC windings on the machine. Now, if practically if you wanted to use some carbon brushes, so certainly this contact over here and this contact over here had to be connected to the stator part, that is actually the carbon, the slip rings over there, and the carbon brushes should be on the stator, and this will be rotating. So this was a problem. So what they have done over here, that instead of providing it with some slip rings and the carbon brushes are on the stator side, what they have done, they have installed a small exciter armature over here. What this exciter armature does is this is a small generator. You can call it as a brushless exciter over here. The point over here is this, that this is a small generator. You can see the three windings over there. You can call this one as the A winding, this one as the B, and this one as the C. And you are actually having A, B, and C windings connected in Y, and they are certainly going to produce some EMF. And that EMF is going to be rectified through a three-phase rectifier, as you can see over here. And this rectified output is going to be supplied to the main field, that is actually the field windings on the road. Now, to make this exciter armature work and to make this exciter armature produce a voltage, you require a magnetic field. Now, stator and rotor, there is always a mechanical motion between them. There is always a relative concept over there. So over here, the first thing first over here is that on the stator side, which is actually the stationary side, on the same shaft of the machine, you are going to produce, or you are going to put three-phase input. That is actually a three-phase input from the grid lines at which this powerhouse is going to be connected. So you are going to give some output input over here, AC phase, rectify it on the stator side, it's a stationary part, and some resistor over there to control that field current, and there is going to be some windings over there, and this winding is going to produce that flux for the rotor, that is a small generator over there. So technically maybe something like this, that you are applying a three-phase supply, maybe 400 volts over here, that is being rectified over there, and after rectification you are actually producing approximately the same 400 volts on the exciter armature over there. We call this one as the exciter. This is very important. This generator over here in this direction, this is called as the exciter, because this is going to produce that three-phase supply, and after rectification this is going to excite the main field winding. That's why the word exciter armature is used over here. So this exciter armature is another generator that is used over there. So this type of scheme, in which instead of supplying a DC supply through some carbon brushes and slip rings, you are doing a three-phase supply to the stator, and certainly there are some diodes attached over there, a three-phase rectifier, and you are having a resistor control over there, just so that you can control how much field you or current you want to give it to the main field over there. So another exciter armature produces that 400 volt or 500 volts, whatever that design may be, and then rectify the voltage and then provide that DC output. Certainly there will be some capacitors also attached, not shown over there, but it will be almost a DC supply, because when you are doing a three-phase rectification, you don't require that capacitor to be very large, so it's not shown over there. So you have just the main field over there, and this is being supplied over there. Now the only problem in this system, as you can see over here, is that there is no slip rings, there is no carbon brushes. The only problem is this: you require a three-phase supply to work over here. And if supposedly at Tarbela and Mangla, whole of the country is shut down, you require still a three-phase supply to supply to the generator so that it can start generating. You can open the valve pumps. You can open the valve pumps of all the water turbines. You can have the water inlet through it. You can make the turbines, the rotor move, but still you require a three-phase supply over here. So a three-phase supply is must. So every generator which has something, a brushless exciter of this scheme, you will always require approximately three-phase supply over there. Now at some plants, they will try to take that from the grid. So maybe the grid is working, some associated plant on the other side of the grid on the transmission line that's working, and it's going to give that three-phase point. It's going to take that current, it's going to rectify it, and then afterward it's going to be producing the main three-phase output. So maybe this is approximately that 11 kV or 13 kV is being produced over there. For those who still don't remember, still have no idea, the Tarbela Dam generator, or in fact, sorry, the Mangla Dam, I don't have the idea for the Tarbela at present. The voltage being produced line to line at Tarbela, this is the voltage at Tarbela over here. So this is 13.8 kilovolts. This is the line to line voltage produced over there at Tarbela over there. Now the problem here again with this diagram is this, that you still require a three-phase supply. So maybe you will have to have some standby diesel generators, or maybe you will have to take something from the grid. But this is a big problem. Why this is a big problem? Maybe the whole country is blackout, just like if something happened, if I remember, it was happening in 2006, 26 September, that was a blackout over there. And that blackout was very huge. The whole country was shut down, and it approximately took 6 or 10 hours to actually make all the generators work over there. And certainly when you're talking about hundreds or 200s of generators working in Pakistan, they all should be producing the same frequency. Then you can join them. This chapter we are going to talk about that stuff as well as the time comes over there. But overall, this synchronous generator over here has also a problem. So how we are going to solve this? This is very important. Now this is going to be solved by a scheme called as pilot exciter. Okay, now you're going to solve that problem with this pilot exciter. Now what you're seeing over here is, now instead of that two-stage diagram, this time it is actually a three-stage diagram over here. The same generator is over here, that is actually the main synchronous generator. This is that brushless exciter which we just talked about in the previous diagram over here at this point. And now this time there is another small generator over here at this point. And if I zoom in over here, the only thing changed over here is this is called as a pilot exciter field. And what you are doing over here, on the stator you have a pilot exciter armature, a three-phase winding done over there, which is again being rectified, which is again being converted into a DC supply, and that DC supply is being through an inductor or certainly a winding, and that winding is actually supplying to that exciter armature over there. So how this stator over here, or this pilot exciter armature, is actually producing, you are using permanent magnets over there. So there are certainly some permanent magnets installed on the rotor, and those permanent magnets are certainly going to be some neodymium magnets or alico magnets, which are going to be something very, very good, and they can actually withstand the temperature, the heat, the vibrations and all that stuff. So they are not just going to be ceramic materials or some naturally occurring. There will be certainly some of the artificial also magnets installed over there. So those magnets, alico or neodymium or some alloys magnets, they will be applied over there, and that are going to produce, maybe now since they are permanent magnets over there, the voltage that is going to be produced may be just like 100 or 200 volts, not more than this, because magnets don't have that much power or that much magnetic field strength or B, so that it can produce that much of voltage. But this 100 volt again rectified through a three-phase rectifier, and then this volt there, this is going to provide that necessary flux, and this time then this is going to produce that 400 volt, and then again it's rectified. Now you don't require any three-phase supply from the grid. You don't require any diesel generators. So this is very important. So this type of scheme is called as a pilot exciter scheme. This is the first generator over here which we are talking about, this one. This is called as the pilot exciter over there, and then this produces a very small voltage, maybe like 100, 200 volts. This can vary depending upon the design. So this is going to supply to the exciter armature. We call it as an exciter. I told you that this is called as exciter because this is going to give supply or excite the main field winding. So this is going to be the exciter over here. So when you are talking about this one, so certainly this one, this scheme over here, as I just told you, this is the brushless exciter scheme over there, and this one is called as the pilot exciter scheme over here. So in this way, you can actually avoid carbon brushes, you can avoid the slip rings, and in this way, the big generators, they can be actually made having a very large efficiency because there is no erosion, there is no contact between the practical parts or the moving parts and the static parts over there. And this way, you can get an easy output from here, that is the A, B, C phases output from the stator over there, which are the three-phase windings connected in Y. One thing very important over here, as you can see over here, all the generators, as you are seeing in this diagram, their armature windings, they are connected in Y. Now that has certainly some advantage over there. We will discuss it very in this chapter. We will discuss it a little late afterwards. But for now on, normally you will always find 90% of generators or 95% of generators connected in Y. There is a reason, because the neutral point is actually grounded over there. We'll discuss this one in detail when the time comes over. Okay, now since we have talked about the types of synchronous generators, we have talked a lot about the synchronous generator, the working of it, how it's going to produce, and we have just found out that the EMF that is going to be produced, if you remember, the EMF produced in a DC generator formula was K phi omega. The same is very true for over here. I'm not going to go in the detail of this one over there, since K is the machine constant, flux phi is being produced here by the magnetic field on the rotor or the field winding, and omega is the angular speed over there, which is being provided by the mechanical source of the prime mover. And since the mechanical speed has to be constant, because this is going to be very critical for the electrical frequency that is being produced over there. So one thing very, very important, that omega or the speed n, whatever you are using, either you are using a revolutions per minute or omega, that is radians per second, whatever units you are using, they has to remain constant. If you're talking in terms of RPM, and if it's a two-pole machine, you will always require 1500 RPM for 4-pole. If you're using for a 2-pole, you will require a 3000 RPM constant speed, unless and otherwise you are not going to get a constant frequency as an output. So the only thing by which you can actually change the EA, or actually the induced EMF of a generator, is actually the flux phi. So this is very, very important, that the flux phi, which is actually being given to the rotor over here, in this case by certainly a pilot exciter or a brushless exciter, whatever that scheme may be. So this is very, very critical. So by changing the EMF, the flux over there, you can change the EMF. So EA over here is actually the induced EMF inside any of the three phases A, B and C. Now beyond this one, now we are going to go towards the next topic of this chapter, which is very, very important, and from which topic we are going to actually talk about the total. So this is called as the equivalent circuit of the synchronous generator. Since just like we did it for the DC machine, this time we are talking here for the equivalent circuit of a synchronous generator. Now, in a DC machine, if you remember the DC machine, we talked about a DC machine in terms of armature resistance. This was a DC machine. There was no inductance involved, because we were always assuming that the DC machine was working at steady state values. So certainly the equivalent circuit of a DC machine was just involving the armature symbol, and then there was a resistance over there. And if it was supposedly a shunt generator, then you had a field winding, and that field winding was having some resistance, and it was having some inductance over there, but it was of no use actually, but because we were having a DC supply, so our inductor behaved as a short circuit. But this time the problem over here inside this synchronous generator is this: it's going to be somehow the same shape or the same equivalent circuit somehow, but the problem here is that this time it's an AC generator. You are producing an AC output, and that AC output certainly is going to be having some inductance effect over there, because this is an AC generator now. So the first and foremost effect of this one, which we are going to model it, the first and foremost effect, the first thing is that you are going to have the resistance of the coils. So the resistance of the armature coils, you are going to model it, and certainly there is no difference over there. The resistance either at AC or DC, there will be some difference over there, but we are not going to take that into consideration. So the resistance of the coil will be RA, and certainly it will be per phase. The second thing which we are going to model is actually the self-inductance of the coils. So this is the self-inductance of the coils, which symbol we will talk about a little later over there. And the third thing is very, very important, for which actually this article is actually going to be paving the way, is this: that you are going to have the distortion that is going to be created in the air gap, distortion of the air gap magnetic field, which is produced due to the stator magnetic field. Now what is this I am talking about over here? If you remember your DC machine, there was an armature reaction, and that armature reaction, what it was doing, that armature reaction was changing the orientation of the magnetic field direction. The magnetic neutral axis was changed, the magnetic axis was changed. This time, when the stator, since it has a three-phase winding, and that three-phase winding is going to be producing an EMF, and that you are going to connect it to some load, there is going to be a current flowing through that A, B and C phase. So if I go back over here for this diagram, supposedly, let's just concentrate on the cylindrical pole rotor over there. So when you are going to connect some load over here at this A, B and C, you are certainly going to get some problem over there. What is that problem? That problem would be that since when this dot 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 and cross 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 are going to have some current flowing through them, it will produce a magnetic field of its own, and that magnetic field will interact with this rotor over here, and when it will interact with this rotor over here, it will produce the magnetic field in the air gap distorted. Now why I'm using the word distorted, because if you remember, in DC machine the magnetic field was in one direction, it was produced because of a static poles over there, so it was a constant magnetic field over there, it was not changing, it was not moving. Here the magnetic field is moving, and how it is moving? It is moving with the speed omega over there. So the problem here is this, that when it is moving with the speed omega, and then there is a stator magnetic field also being produced over there, and when it is going to change it, it's going to change its phasor orientation. Again, this is the phasor orientation because I am talking about an AC generator at present over there. So now these three things, very, very important, and these three things have to be incorporated over here. So this third thing, you can call it as the armature reaction in a synchronous generator. This is the armature reaction of a synchronous generator over there. So we are going to model these three things in a synchronous generator equivalent circuit. The fourth thing, which is actually not done here in this book, but if you go to your appendix C of your chapter Chapman book edition number 5, you will find out that the fourth thing is that you have to take into consideration the armature reaction effect is going to be different when it's going to be a cylindrical one, and the armature reaction is going to be different when it's a salient pole one. Why is that so? Because in a cylindrical pole one, the uniform air gap is there. So when there is a uniform air gap, you don't need any problem. Everywhere the effect is going to be the same. But when you are going to have something like this over here, a salient pole machine, here the air gap is different, here the air gap is different, so certainly there are going to be two types of effects over there. One effect at this point, one effect at this point over there. But here in your book they are assuming that all the generators with their discussion are actually cylindrical pole rotors. So practically they are assuming that all the cylindrical pole machines are actually only covered in this book. But if you are interested, you can go towards the salient pole machine as well. Now before I move on forward over here and we talk about this synchronous generator proof over there, this is actually the same picture I have over here. I've taken this one from the book over here. Now if you concentrate your attention on this first picture over here, this is very, very important picture. This first picture, let me call this one as A over here. So what you can see over here, now this is a little mistake over here from maybe the book part over there, because they have told over here that this is going to be a cylindrical pole rotor, but they have taken a salient pole over here in shape. So but you can assume that it's actually a cylindrical pole one, so but they have shown over here as a salient pole one, but the proof is approximately the same if you don't consider it very accurate over there. Now if you see over here in this first diagram, what is happening over here, this is a rotor, and certainly there will be some windings shown over here which is not there shown over here. Certainly that winding, if I show it over there, this will be something over here like this, and that winding will be certainly connected to some DC supply so that it can produce some north pole here and a south pole here, and certainly this is rotating with a speed omega m over here. Now when this is rotating over there, these three are going to be dots and these three are going to be cross. You can name them as A, this is going to be A dash, this is going to be B, B dash, this is going to be C, and C dash. This is actually figure number A. Don't confuse this one with other one here. Now, when this is BR, since this is again the topic is going on towards that BR and VNet and all that stuff, I hope you have gone through that induction motor topic very carefully. Now, this is BR, which is actually being produced by the rotor. So, this BR is here, and it is going to produce an induced EMF inside these three conductors, which are A, B dash and C dash. So, this certainly means that you are going to have some EA maximum also. Now, what does EA maximum means? This means that when this is aligned over here in this direction, your EA max is also in the same direction. This is actually since EA is actually an AC induced voltage, so EA max is directly in phase with BR. So wherever this BR is moving, in phase is actually EA max. So the sinusoidal EMF induced inside the A conductor, because A is actually the closest conductor over there in this machine. So in A conductor, your EA is going to have the maximum magnitude, that is actually the peak of a sine wave is being produced over there. So this is EA max. Now in this machine over here, if this machine is not going to be connected to any load, supposingly this is a machine with A dash, B dash, C dash, these three windings or the three phase windings are not connected with any of the machines. This means that your V phase is exactly the same over here like this. Why? Because when the machine is not running, your V phase, which is actually the terminal voltage or the output voltage of that generator. Please remember, when I'm using the word V phase, this is actually the phase voltage over here. I'm not talking in terms of three phase or line to line, because again this is a three phase machine, and any equivalent circuit which we are going to draw over here is always going to be on per phase analysis. So whatever circuit diagram we are going to do it's always going to be on per phase again. So this V phase, when the load is not connected, it's exactly in the same orientation as VEA. But now when you are going to connect an EMF, now when you are going to connect a load over there, and again this load is going to be attached. Now normally 90% of loads in daily life, they are lagging. So what will happen, I still don't know where will be V phase, but what will happen over here, that EA is actually the induced EMF inside the generator, that is actually this A winding over here. This is A dash. Let me use some different colors so that it's actually healthy for the whole diagram. This is B dash, and then certainly this is the C over here. This is C, this is C dash. So now if I use another color over here, let me just use another one. So what is happening over here, this is EA max, and since the load that is connected is actually lagging, so it is lagging behind the induced EMF, that is IMF. The lagging nature of that, you can find out this angle will be certainly some theta angle. So whatever that inductive nature of that load, maybe it's having a power factor of 0.7, then at 0.707, then this theta angle will be 45, but certainly it will be actually having a lagging nature over there, because 90% of loads, they are lagging. Even the wires are also going to have some inductance over there, so this current is going to be lagging. Now one thing very, very important, we still don't know where is V phase. We still don't know where is V phase. So this IA max is actually the peak value of the current, because this is lagging behind the EA voltage waveform because of the load that is attached over there. So this EA is actually going to produce a magnetic field of its own, and this magnetic field is going to be produced by the stator winding. These windings over here, this winding, this winding, this winding, or this winding, or this winding, or this winding. So there is a current flowing over there. I am assuming that the three phase of the machine, they were loaded balanced, they were loaded equally. So what is happening, there is going to be an a magnetic field at 90 degrees to this one over here like this. So IA, which is exactly lagging behind the EMX, the BS, we all know, we have done this one in your induction machines proof over there as well, that the current that is being produced, or the magnetic field, sorry, is being produced over here, that is BS over here, and this BS is exactly at 90 degrees. You can see the orthogonal over here. So this BS is being produced over there. Now this BS is actually being produced, where this actually BS is being produced inside the stator, and that is going to link with the rotor magnetic field. So what is actually going to happen, that BR plus BS, they are going to add together vectorically, and you are going to get some B net. But how that B net? That B net is actually going to be the net magnetic field after armature reaction. So if this one was BR, you are going to add BS with it and you are going to get B net. But let me just break up the whole scenario over here. If BR produced EMX, can we call that BS is going to produce an EMF over here, which we can call as E stat. Just like over here, there are two magnetic fields now. Certainly they both are moving with the same speed. One, the main magnetic field is BR, and that is producing an EMX over there. The next one is BS, which is actually being produced because of the current flowing inside the armature winding, and that is being produced at 90 degrees to the IMX vector. So that BS produces E stat over there. So practically we can say that your magnetic field, or the per phase voltage V phase vectorically, is equal to EA plus E stat. I hope this is clear over here. I'm again repeating. Since there are two magnetic fields over here, one is called as BR, that is actually being produced by the rotor. We are giving a DC field or a DC current to the electromagnet over here, which is rotating with the speed omega, that produces EA. That is actually over there. If the machine is not loaded, that will be EA, that will also be V phase. But if the load is attached and that load is ER lagging load, what happens? It gives rise to an IA, that is IA max over there. And because of that IA max, I have a BS magnetic field, and that BS magnetic field gives rise to E stat. What is E stat? E stat is the voltage induced inside the stator windings because of the current flowing. So you can call it as something, a self-induced EMF over there. So technically or vectorically, you can call it that V phase is equal to EA plus E stat, the vector over here as well. Now if I move on towards the third diagram, the same third diagram which you have just drawn over there, you can see this is EA max. This is IMX, there is an angle, certainly a lagging factor over here, theta. And then this is BS, BS is shown over here, very small one. Now the point over here, I have shown it a little bit large over here, as you can see over there. Practically it will be very, very small. Reason over here, very important one, because there is an air gap. From the stator, the magnetic field has to reach the rotor, and then it has to distort the main magnetic field, BR. So this BR and this BS, so this BS vector, when it is going to be placed here, and then if I make it for like supposedly the other direction, so this one would be my B net over here. So there will be a slight change over there. BS will not be that much. Why? Because there is an air gap, and you all know that air gap is not a good conductor of the magnetic field. So BR plus this one is the BS over there. So you are having vector addition of BR plus BS, you have B net. Now if you, this is by the magnetic field addition over there, but if you want to go it by EA and E stat, with this EBS you have this E stat over there, which is actually called as a subscript stat over there, because this is induced inside the stator. So when you have this E stat over there, this is the same diagram over here. If you can see in this diagram, you have your EA max over here, you have your IA max over here because of the load, then you have your E stat over there, and when you have this EA max plus your, or EA simply, but E stat, you have your V phase over there. And if I zoom in over there, this V phase is exactly in phase with this B net. What is B net? B net is the net magnetic field inside the generator that is produced because of BR plus BS. These are all vectors over there, so I don't need to have arrows on this one. The reason behind over here is this, that these are actually bold over there. So V phase is equal to EA plus E stat, or B net is equal to BR plus BS. So what is happening inside your machine, that when the load is connected over there, you are having a current. That current is lagging in nature. That current produces BS, and that because of that BS, you have actually E stat voltage produced over there. That E stat plus the induced EMF because of the main field actually gives rise to V phase. So what is happening actually? V phase is going to be a lagging. So what is happening, that V phase is going to be lagging. So what this actually tells you, that V phase is actually going to lag behind EA next. And if you remember, whenever you are modeling anything, you all have three elements over there. You have a resistor, you have a capacitor, you have an inductor. And there is only one element which produces a lag, that is an inductor. So you are going to model this armature reaction with an inductor. But how you are going to model it still? Let me go with mathematically over there. Now when we are talking about this E stat, what is this E stat? Is this E stat proportional to IA? What is IA? IA is the phase current over there. So if current is more, yes, certainly BS would be more. When BS would be more, E stat would be more. And can you tell me what is the E stat over here and what its orientation? The orientation is of E stat is this, that this is completely at 90 degrees to lagging behind IA. It is completely lagging behind IA. So you can call it that E stat is at approximately minus J angle. What is J? J means 90 degree forward, but here you are going backward over here. So this means E stat is exactly at minus 90 to IA. So using this cost proportionality over here between IA, can I call that E stat is equal to, I'm going to change that proportionality into another constant over there. So this can be called as minus JXIA. So E stat is going to be called as minus JXIA. What is this X over here? This is actually the armature reaction or the machine constant. Now this is going to be machine constant. Why? Because it is dependent upon what? This is dependent upon the air gap. This is dependent upon the material used over there. If maybe the stator and the rotor, they made up of two different materials, so certainly there is going to be a difference from the stator to the rotor. The EMF is, or the flux is going to travel differently. They are going to have different B or different materials, and certainly this X will be different over there. So this is the machine constant. This is dependent upon the machine design, the machine dynamics. So what is E stat? E stat is equal to minus JXIA. So this is the armature reaction constant over there. Now if I'm only modeling, if I go back over here, the first three, what was it? They was having a resistance, I had a self-inductance. What I have done, I have just done this distortion of the air gap magnetic field. So when I have this distortion of air gap magnetic field due to the stator, magnetic field, so what I'm talking about, sorry, I'm talking about V phase. What is V phase? I'm not going to draw the vector symbol over here, so I hope everyone can add the vector symbol of yourself. So this is EA plus E stat. So when I have this V phase, or let me just put on for just a beginning lecture, so this will be easy. So this is EA minus JXIA. You can call that. So what I have done just now, I have only modeled the third parameter, which is actually XIA over here, which is JXIA, is actually the armature reaction over here. So in this equation up till now, how I can model this is actually the equation which has formed now. So if I want to just take this equation and I want to make my circuit diagram or the equivalent circuit, what this means, what is EA? EA is the induced EMF. So certainly I will be using something, a same picture just like your DC machine, and with this over here I will have a inductor because this is X over there, that is the same constant over there, and then over here I can call this one as V phase. So this is EA. This is the current which is going to flow out of this generator, and this is that JX over there. So if you want to now model V phase, what is this? EA minus JXIA. So this is just a simple model over there. Now this has only this equation over here, it has only yet modeled only the armature reaction. Still two things are remaining. What is the two things remaining are? If I go back over there, one is the resistance of the coil. I told you this is actually RA, and when I'm talking about the self-inductance, that is going to be modeled as XA. since A is the name subscript being used over here for different windings. So I have EA a subscript for one phase. So now what is going to happen, this equation over here is going to be changed. So when I'm going to add together, so this one would be EA, again I'm going to add the vector form over here. This is minus JXIA, this is the armature reaction. The next, this is JXAIA, this is the self inductance of the coil. And then the last one, which is actually IARA, the resistance of the windings. So this one is actually the main equation where all the losses are modeled for a synchronous generator. So now what happens, this diagram which you have just done over here, this will change to, if I just model it over here again, this is the same EA just like we used for the DC machine, and then here the first thing is the inductor, that is X over there, and then I have the inductor over XA, and then I have the resistance over there. So this is the per phase, so this is EA. Since this is a generator, current is flowing out. This is very, very important, please don't make this mistake. The current is always going to flow out over here. So the EMF voltage or the phase voltage over here on the output terminal, this is the same output terminal which we can call it AA dash or BB dash or CC dash. Again, this is the per phase analysis. This is that RA, this is that X and A, and this is that X. So this is the final equivalent circuit of your generator. The rotor, the stator side over here. I've still not drawn the rotor one. Rotor is just going to be a DC winding given to a DC by a DC supply over there with some winding, certainly some inductance if it's going to vary by some transient state over there, but otherwise this is over there. Now normally whenever any manufacturer, they are combining or giving you the value of X and XA, they combine these together and they give a value called as XS, and they call it as the synchronous reactance. They call it as the synchronous reactance. So instead of giving them X and XA as two different values, they just give a value of XS. They call it as a synchronous reactance. So what happens now, the whole equation or the circuit diagram now is actually just one inductor, and then there is just one resistance over there. This is that XS, this is that RA. The current is going to flow out of this generator. This is that EA, and this is that V phase over there. This is an AC EMF over there. Now in this diagram, if you want to actually have the rotor also added, so on this side over here, supposedly this is that resistance, and then this is that winding over there. This resistance can be that field winding resistance over there, and here you can call this one as the DC supply applied over there. So this over here is actually the rotor, and this one over here is the stator equivalent circuit over here. Now this is just for single phase over there. You can call it as A dash or B dash or C dash over here. But again, this is the per phase analysis over here done like this. So this is the equivalent circuit over there, and the equation as now, since this was the equation over there, so for this same circuitry over here, the equation actually becomes equal to, let me write it down again, this is V phase. So this becomes equal to EA minus JIA XS minus IA RA. So this is the equivalent circuit of your synchronous generator, and this is the equation over here, that is V phase equal to EA minus JIAXS minus IARA. XS is the synchronous reactance, and this is called as the synchronous reactance, including the self-inductance of the coil and the armature reaction constant over there, like this. Now one thing very, very important. Okay, now since we have just done this equation over here, this one, that is V phase is equal to EA, and I just showed you the equivalent circuit with XS and RA over there. If you want to repeat it for the three phases, this is the actual repetition over here on this side. As you can see over here, this is the rotor. with RF and LF as the resistance and the ducts of the winding, or the field winding actually, which we are calling it. Then you are applying supposedly certainly a DC supply over here. So this is going to be that DC supply. This is the adjustment resistance, just like you are going to control it. If you have done the DC machine experiments in the lab, you are fully aware that by changing this R adjustment, you can actually do this one very easily by changing this R adjustment resistance. The field current changes. When the field current changes, the flux changes. And now here, since this is all three phases, instead of writing is EA, EB or EC, what they have done in the book, this is picture is taken from the book. So this is EA1, and then in the second diagram you have this as EA2, and then in the third diagram this is EA3. The rest of the parameter JXS RA, JXS RA and JXS RA, they all are same, nothing changed over there. So sorry about it, I just crossed it. So this is JXS RA over there, and this is V phase 1, and then there is V phase 2, and this is V phase 3. If you are talking about a machine that is completely symmetrical and balanced, and if you are going to connect it as supposedly as Y connected, supposedly if you are going to connect it as a Y connected or star connected, this means that this point, which is actually the A dash, this point is actually B dash, this point is C dash. You are going to combine this together, and this is supportingly going to be connected to ground. So you are going to connect it to ground like this. And this one is going to be A phase, this one is going to be B phase, and this one is going to be C phase over there. So in this way, the windings are connected in Y or in delta. So you are going to get V phase, VB, or VA, VB or VC. Now generally speaking, we use the word V phase over here. So when we are talking about this one as V phase, so we are actually referring to the phase voltage, which is actually VA, VB or VC. Same thing over there. But when we are going to measure with a voltmeter, this is very, very important. When you are going to measure the voltage between any two phases, this means this is actually V line to line voltage. And technically speaking, this line to line voltage is going to be actually called as the VL, or we call it as the VT, and this will be under root 3 times V phase. This is very important. These three symbols are normally used for the line to line voltages, but if the symbol used in any of the expressions or n problems or any expression, it's used as V phase, this is actually simple single phase. This is the same expression which you already know, that is V line to line is equal to under root 3 V phase over here. So when you are having a machine connected in Y configuration just like this, you have terminal voltage. This is VT, terminal voltage. When you are measuring between AB or maybe BC or measuring between CA, then this is called as terminal voltage or line to line voltage, and this is under root 3 times V phase over there. So when you are going to have okay, so if you are going to have a Y connected machine, as you can see over here in this diagram, the three circuits, they are connected now in Y configuration. Their negative points over here, this is actually going to be the ground, and this is actually that A dash, B dash and C dash. And if you are measuring the voltage between any of the two terminals over here, supposedly this is A, this is B and this is C. So if you are measuring the voltage between A and B, this is VT, and this VT is actually equal to under root 3 V phase over here. So this is actually your Y connected synchronous generator. And if you have supposedly a delta connected generator, then this is something like this. You can see all the three windings of the three phases, or the three equivalent circuit of three individual phases they are. So if you can notice this one, this is the negative end. Supposedly if this is A dash, this is A, and then this is that B dash, and then this is B, and then this is C dash, and then this is C. So you can connect them in delta configuration. This time, even if you connect VT, this is going to be the same V phase over here. Why this is so? Because if you remember, line to line voltage is equal to the phase voltage in your delta connected circuits over there. So this is the equivalent circuit of a synchronous generator. Again, a rotor diagram has not been drawn in these two circuits which I just shown you, but if you want to draw it, you can just add this rotor diagram which I have just shown you over here with this R adjustment resistance, RF and LF over there. Now, one thing very important before I want to actually close this lecture over here, which is very important one. I hope everyone has followed this one up till now. If I have this equation which I have just done, which we have just written as V phase equal to this is EA, sorry about it, EA minus, I'm just writing IARA first, minus JIAXS. It's totally up to you. You want to write the XS term first or whatever. Now, if I even miss this arrowheads from now on, please pardon me for that. Maybe you can add it yourself. Now, when you have this equation, now here I want to draw the phasor diagram that we have done in your CAD course also. Now, before we want to go on move towards the phasor diagram, one thing very important, these negative signs. These are a little difficult to draw on the vector sum or the phasor sum. So what we are going to do, this is EA equal to, I'm just going to rearrange this one. So this is V phase plus IARA plus JIAXS. Now, why I'm doing this? I'm doing this because here I can have a reference phasor and I can draw this one. Now, all the subtraction symbols have been changed to the plus one. So this is very easy for me. Now, here I am going to take V phase as my reference. This is very important one. Now, please pay attention over there, because this chapter is now going to be based on this equation, and all the phasor diagrams which are going to originate after this lecture, they are going to be based on this equation over here. Now, the first type of load we already we've talked about previously also. The first type of load is called as a resistive load. So this means that I have to draw the phasor diagram of this equation, that is EA is equal to V phase plus IARA plus JIAXS over there. I have to take one reference phasor. What is that reference phasor? Let me take that reference phasor as V phase over here, but certainly V phase is actually going to be the output. But since I just want to draw the phasor diagrams, so this is very important. So what I'm going to do, I'm going to take my reference phasor as this as V phase. Now, when I'm going to draw the next one, this is very important over here. So the next thing, what I have to do, since this is a resistive load, what I'm going to have, the vector IA is going to be exactly in phase with V phase, because this is a resistive load. So IA will be, this is the voltage across that load per phase voltage, and this is a resistor over there. So IA is completely in phase with that phase voltage. IA is the phase current. This is very important. So what happens now, the next vector is that is going to be added over here. If you see this equation of V phase, the next vector is IARA. So what I am going to do, since I know this is IA, so the next vector is going to be just head to tail rule addition. So this is IARA, like this. So what I have done, V phase plus IARA over here. What is the next vector? Next vector is JIAXS over here. Now J, this means that I have to move it in the positive 90 direction. Let me use another color. This is very important. Please use different colors whenever you are doing it for your exam or whatever over there, because that actually makes the diagram more legible, because there are a lot of phasors going to come. So the next vector is the 90 degree angle vector, which is actually JIAXS. It's 90 degrees. So what I have done, V phase, IARA plus JIAXS. So now I have added these three vectors, and now the last and the least very important one, the EA vector will be from this point over here up till this point, and I can call this one as EA vector, and this angle is delta. Now this angle delta, you can make this a little up over here. This is a little mismatching over here. So this EA and V phase, there is a delta angle over here. This delta angle is actually called as the torque angle over here. So this delta angle over here, if I just go back a little over here on this diagram which we have done just before, this diagram over here, if I just go in over there, this angle over here between EA and V phase, this diagram angle, this is the same delta over here. This EA max and V phase, then it will be the same delta angle over here. So you can see V phase, EA is leading behind V phase over here. Now if I go back over there, let me just go on towards the same resistive load. So this is the phasor diagram for a resistive load. Now the second diagram, let me go on towards the second type of load, that is the inductive load. So when for inductive load, I have an inductive load. If I draw the same vector, same like this thing, this is my V phase, and this is going to be the current vector, since the current is lagging in an inductive load. So what is going to happen? This is going to be IA. This is going to lag by an angle theta over here. So what happens now, the next vector which I have to add over there, if I, let me just verify, I have to use the yellow color actually over here because I just want to keep the same over here. So IA RA is going to be just parallel to this IA. So this is going to be that IA RA, and the next vector is going to be that green color. That is going to be IA axis. So this is going to be that JIA axis 90 degrees to this one. And when I add this together over here for the EA vector, so this is the EA vector over here. So this is that delta angle over here. So you can see now for the resistive it was something different, for inductive load this is very different over there. And then the last part, this is the last phasor diagram. So we all know the last type of load is actually the capacitive load over here. And normally these loads are not that much in vogue. Why? Because normally capacitors are never there. So for the same phasor diagram, the first phasor reference, that is V phase, we draw this as V phase over there, and this time now the current phasor is going to be leading. This is very important. So the current phasor is going to be leading, so this is going to be an angle theta leading the V phase angle. And now this time when I'm going to draw the IARA vector, this is going to be like this. This is going to be IARA vector like this, and the JIAXS over here, this is going to be here like this. This is going to be JIAXS. This is going to be that 90 degree angle. And the last but the very important vector, which is actually going to be here, this is going to be that EA vector, which is this angle delta. So what you are seeing over here, this is the capacitive load, this is the inductive load, and this is the resistive load phasor diagram over here. Now if you notice over here, in resistive load, the difference in magnitude of this EA and V phase is there. But if you move on towards your inductive load, the difference is huge. The EA is approximately double over here as compared to your V phase. And the reason over here is this, because when you have an inductive current, that inductive current is flowing through an already inductive armature reaction model and the self-inductance of the machine, so it's having more difference. But if you move on towards the capacitive load, it's a little different scenario. We will discuss this in much detail in the next lecture, that with the capacitive load how it changes, and with this angle theta changing over here. So this is IA leading, it can angle change so that EA can be now greater than or smaller than V phase. If you remember your transformer phasor diagrams, we did the very same three phasor diagrams in same proportion in the transformer also. So this is just over here for the today. Today we have covered from chapter number 4 from article 4.1 to 4.5 over here. Next time we are going to do something 4.6 to forward on. So this is going to be over here. Today we have discussed over here in much detail the synchronous generator, which is actually also called as an alternator. We have discussed its equivalent circuit. We have discussed the types of synchronous generators. We have discussed how you are actually going to avoid carbon brushes and slip rings, and how you are going to have it run for a steam turbine or maybe for a hydro turbine or any other type of a generator that can actually be used over there. So this is all from today's lecture. This file, this PDF file, I will be uploading them on my website. I hope so everyone, those of you who are still not familiar, I will be uploading this website at ep.nge.com.pk. This lecture, I will be uploading them on my YouTube channel every time, maybe on MS Teams also if it is easily, because I always want to have the 1K or 2K image over here, because this is a screen grab over here. So any questions, if you have any questions, go to your question and answer sessions, or afterwards you can email me, or maybe in a chat window if you have anything specific related to this PDF file, or maybe the lecture which we have just done. Okay, thank you. Allah Hafiz.